So now we move to something different from modeling. As I mentioned to you, that we are talking about two parts of the discussion, modeling and analysis. I think we have spent some time on modeling, and the remaining modeling we will see on the actual program. I want to talk about the analysis part now, which is the understanding of the way the model will be analyzed. So if you remember, we started with this equation I showed you, structure, forces, displacement, spring. So we talked about this, and at that time I told you that this equation F is equal to KU is not enough. We need more than that for a proper analysis, for an advanced analysis. This is good enough for simple analysis, for gravity load, maybe good enough for live load, something like that. But when it comes to wind, earthquake, moving loads, other things, then it's not good, not complete enough, because we said that this is static, dynamic, elastic, inelastic, linear, nonlinear. That equation that we just saw is only good for static, elastic, linear structure. That's it. It does not apply to other situations. So when the load is not static, is applied in a fast manner, or the mass is moving, then that equation does not apply. Also, when we have a nonlinearity, strength, degradation, collapse, all of those things cannot be determined by that equation. If you want to do all that, we need more. So there are 8 types of equations. But let's look at this guy, the doctor, medical doctor, right? So you're too young. I hope you don't go to the hospital for checkup. But when you reach my age, we have to do that every 2 years. So when we go to anything, if you're anything wrong with you or anybody, when they go to the doctor, what is the first thing they do? Blood pressure. They take you to a room, check your blood pressure and pulse. You know, this tracker, if you're wearing that, it also tracks the whole day your heartbeat. Right? All the time, what I'm doing, everybody's doing, then it can track your heartbeat, plot the graph, and show whether the health is good or not good, whatever. You know. So this kind of thing, that means we have some kind of a heartbeat or tracking of human beings. Do we have the same thing for structures? Do the structures have a heartbeat? That is the question. And that is which means the dynamics of the human body or things is very important. So check blood pressure and heart rate is the first thing they do. Can we do the same thing with the structure? Do we have something that we can say, okay, I have checked, and when the doctor checks and they say, oh, your pulse is okay, your blood pressure is okay, you're fine. Nothing immediate. So anything immediately wrong is detected by those two things. So can we have something in a structure that we can also check in the same way? So when you want to check how fit you are, they put you on a treadmill and then you run. And then during that running, they plot many things for you. And after that, they say, okay, you're okay, not okay, fit to run marathon, something like that, right? So that means there is something that the doctors can measure and determine everything about the human body by just 1 or 2 indicators. Dynamic response of a structure is actually the heartbeat, as the blood pressure of the structure is the same thing. So every structure has a heartbeat and a pressure and a pattern that we can also determine, and we can make same kind of decisions about the structure that the doctors can do about human beings. If we know how to listen to the heartbeat, if you have the stethoscope and you know what it means, then you can learn a lot about the structure. You know this one, right? Physics. Newton. He said that F is equal to ma. Force is equal to mass into acceleration. For Newton, the body is rigid, cannot deform, and its body is, if you move a body, it remains the same. Force cannot deform the body. That's his assumption. That's why the force, mass, and acceleration is enough for him, not for us. Because we are dealing with bodies that deform, that change, and then we need something more. So we need to add more terms to this one. We have one equation already, F is equal to Ku, stiffness and displacement. And Newton is saying F is equal to ma. So we have two extreme cases. In F is equal to KU, we are assuming there is no mass, there is no movement, there is no acceleration, and Newton is assuming there is no displacement, there is no deformation, no stresses. So we have to combine these two things together. When we combine them together, we get this equation. So this is the complete equation of a body, including Newton, including us. Engineers and Newton get together, and this equation is the complete equilibrium equation, where you have mass into acceleration, F is equal to ma, and then you have K into U, stiffness equation, and we also have the other one for damping, which is a property that we will see later also that needs to come in. So we have the complete equation, which means the force is equal to this plus that. Mass into acceleration, damping into velocity, stiffness into displacement. So you add all these three terms together, then it becomes equal to the total external force. So part of the force is resisted by mass, part by damping, part by stiffness, right? So this is the complete. So if we understand how this equation works, we can then solve any problem in structural engineering except one. Which one is not complete yet? What is missing in this equation? Nonlinearity, damage. This is still assuming that the structure is infinitely strong to resist every displacement, every force generated on the structure. So it does not include nonlinearity. It is still applicable to linear system. So it's a linear dynamic equation. The first one was linear elastic equation. This is linear dynamic equation. The first one was linear static equation. This one is linear dynamic equation. Nonlinearity is still missing because this is still assuming that the structure can continue to deform infinitely, never break, never fail, never collapse. So it's incomplete still, right? Never degrade. So that force is actually spring that we talked about, and the one on the left hand side is the mass and acceleration. Now this mass into acceleration and plus others, the stiffness matrix out of that in this portion that we are talking about, actually this to be here. So the stiffness matrix actually is coming from cross section, member, structure, section stiffness, member stiffness. You have talked all about that, right? So stiffness, this arrow is wrong, this should be here. So we are talking about stiffness. So stiffness is the main property that model gives you. When you create a model, it gives you the information about the stiffness because you give material property, you give cross-section dimensions, you give the connectivity, you give the member length, you give everything, size. So stiffness is basically calculated from the model, right? And after you create the model, then that model also has mass and also has damping automatically, whether you provide it or not, it's there. Because all physical bodies have mass and all physical bodies have damping. So which means that when you create a model, whether you include this information or not, whether you consider this information or not, it's present automatically. But you choose to ignore the mass and damping in simple analysis. But in complete analysis, we cannot choose to ignore that. So we have to use the complete stiffness, the complete damping information, damping has many components, and complete mass information. Then our structure, model, and analysis will be complete. We also need to see which part of that is linear and non-linear. We have to talk about non-linearity now. Second part, which I told you that's missing. And we know that material has two parts, linear, I mean don't think about, so this is material stiffness has two parts, linear, non-linear. Section stiffness has two parts, linear, non-linear. Everything has two parts, linear portion, non-linear portion. And we spent a lot of time in the previous course talking about the non-linearity of materials and non-linearity of the cross sections. We tried to plot moment curvature curve, we tried to do this stress strain curve, confinement, we studied all that. That was all talking about non-linearity. So we know already or we should know already, these two parts, this material stiffness nonlinearity and section stiffness nonlinearity comes from the modeling of the cross section. Now, how is the two different? This graph also I showed you last time, linear versus nonlinear response. This one is linear and elastic response. That means it's linear. When you go over, it will go on forever, and when you unload, it goes back to the same point. So it's linear, also elastic, right? This is ideal. Most materials behave like this only in a short range. This one is linear and elastic. Goes straight, come back straight, but not in the same planes. So there's a damage, accumulated damage. Every time it goes up and down, it doesn't go back to its original state, so there's a damage here. There's no damage here. Some damage here. Then nonlinear, elastic. It goes up, comes down, nonlinear, but comes back to the same position. No damage, but nonlinear. And finally, it is nonlinear and inelastic. So it is nonlinear going, nonlinear coming back, and also there's a damage. So we are dealing with realistic materials are here, especially reinforced concrete. Reinforced concrete is nonlinear inelastic material. One of the most difficult one to deal with, because if concrete beam cracks, if you unload it, the crack does not heal itself. It may close, but the crack is still there. If you do it many times, it will damage. So that means all reinforced concrete structures, when you load and unload them, they will get damaged. And dynamics is exactly that. It will change the loading during the history. That means the loading is changing, so damage is always there. So if you do not consider damage into the analysis, that means you will never know if the structure is going to fail or not fail. So to understand the failure of a structure or to understand the damage in a structure, we need to study nonlinear dynamic response of a structure, not the one that we normally study, which is okay sometimes, but not okay when we're dealing with complex structures and we're dealing with earthquake and moving loads and even strong wind. So now we come to the complete equation. We add one more term here, which is the nonlinearity. So that is the equation part for linear, and that is the part for nonlinear. So this is the complete equation now. Now nothing is missing. Or is something missing? Anyone suggest that something is missing in this equation? It's a challenge. Can you think of something in structural analysis that is not covered by this equation? So if you have this equation, you can solve any problem in structural engineering. I really mean it, any problem. No matter how complex, it must always come back to this equation. It is part of that equation. Whether it be a bridge, whether it be temperature, is fire, is blast, is earthquake, is flood, whatever you can think of can be analyzed by a finite element model and this equation. The rest is all your skill. How do you use this equation and modeling to solve any problem? So now, this problem of the chair that I was talking to you last time, that it's, if I slide it, depending upon who's sitting on it, the force I apply is different, can be covered by this nonlinearity. So a nonlinear component will determine the additional force I need because of the extra load on it, or the change. If I put the wheels, I can roll it. If I don't put the wheels, I cannot roll it. So that the mechanism can be now accommodated by using the nonlinear modeling. So nonlinear modeling gives us the additional parameter to handle complex behavior. And also failure. Because this value can be negative. So it can cancel out the force carried by other components, and finally the net force carried out may be zero or even negative, depending upon what is the value of the negative, this number, FNL. So that's the external force: mass, acceleration, damping, stiffness, nonlinearity. So that is what SAP and ETABS have. Internally, they just solve this equation all the time. Even when you're applying dead load, they just delete these two parts and this part, and they solve this and that. But actually, they are always solving the same equation. So the analysis procedure is always complete. Sometimes some terms can be zero, but equation is always the same. And nonlinearity itself comes from this equation. That's why it is nonlinear, because this contains that inside it and so on. So it's a circular reference. That's why it becomes nonlinear. So now, why is this a force correction? Nonlinearity, why is it a force correction? Can somebody tell me? Why is this a force correction? Why is nonlinearity a force component? You know, you look at the equation, you must understand the physical meaning of every term. If you do not understand the equation, physical meaning, equation, you will never really realize what's going on here. So what we are saying is that there is a linear portion which is increasing, which all increase or positive value. Mass is always positive, stiffness is generally positive, damping is generally positive, so you always have positive side. Nonlinearity can be positive or negative. And it's a force correction. Now please watch this next graph carefully. This is why the nonlinearity is a force. This is the linear response, blue one, which keeps on going forever. Red one is the real response. So this is nonlinear. So at any given displacement, you can see that there is a difference between linear and nonlinear. Nonlinear can be above the blue line or can be below the blue line. It depends on many things. So there is a difference at every location in the displacement. There is a difference between linear response line and the nonlinear response line. And that difference is the nonlinear component, correction factor, that we apply to come from here to here. So now we're talking about nonlinearity here. So nonlinearity is actually a force difference or correction between linear to nonlinear. And you might say, well, it's very easy to determine. What's the problem here? You have the red line, you have the blue line, find the difference. What's the problem here? Why is nonlinear so complicated and it's almost sometimes impossible to do? Why? Okay, what do you think? That one. What do you think? Why is it so complicated? Seems like a simple problem to me, right? You people are forgetting. We don't know the red line. Red line is the nonlinear response that we do not know. We only know linear. So we can only find the difference between two lines if we know the red line. Red line we do not know. That's the one that we are trying to find. We are trying to find the nonlinear response. We only know the linear response. So we are searching in the dark for the red line. We don't know the nonlinear response. We only can solve the linear response. Nonlinear response we have to find by that. So we don't know the red line and we also don't know the difference. That is a problem. How can you find both? How can you find both? If you are trying to find something, what do? You search, hit and try. You check here, you check here. If I say that the nonlinear response is somewhere in this room, and I put blindfold on your eyes and say, go find it, you will do like this, and somewhere you will hit it, right? You may not hit it if you're not looking in the right direction, but you might hit it. So that's exactly what we are doing. This analysis, nonlinear analysis, is exactly like that. We are trying to find something in the dark with a blindfold and hoping to hit it. But if you are systematic, then you will say, I don't know where it is, but I will go line by line. I will go this way, then I will go this way, then I will go this way, I'll go in a straight line, I will cover so I will not miss it. So by the time you reach, you will find it. But if you just go randomly, you will not find it. But if you go systematically, then somewhere you will find it, right? So that is the way that programs work. So they have they try to start finding it here and try to keep on this line so that they don't go too far from this one. So they try to, in small steps, it is done. So for example, what is done is that the way the program will work is that if it is going to find that, it will not apply, let's say the total force is 100 tons and we are trying to find nonlinear response or nonlinear displacement for 100 tons. For 100 ton is, let's say, here. So a linear response you can find 100 ton and you can find the displacement here, maybe 10 centimeter, right? But we are interested to find 100, okay, 100 is maybe here. So we are interested to find this one here. We cannot find it if we try directly to 100 because we don't know where the red line is. However, if you apply the 100 ton in small increments, 10 ton at each time, then you are here, then here you search in this close, because it's close by, and then you find the red line. Then you remember where the red line was. Then you try to continue in that red line along that. So you try to remain close to the red line, not going too far off. So next time your blue line turns and you are here. Next time it turns like this one. So you keep changing your blue line to be close to the red line. And ultimately you can trace that. So that's why the stiffness keeps changing. So as you know, slope of this line is stiffness. So every step, the stiffness is calculated again based on the displacement and then adjusted. Then next step loading, then adjusted like that. So this is called nonlinear analysis using load stepping, right? You apply the loads in steps. And then you can do this one. So once we are able to do the nonlinear response, then we can solve most of the problems. Let's now talk about another interesting thing. Let's go back to the heartbeat thing. So if we say that there is a structure where there is no load, there is no nonlinearity, there is no damping, only mass and only stiffness. So that means a human being with nothing wrong, just a simple guy sitting there and just one instrument. That means it's not, the person is not, then they take your heartbeat, you have to sit down, right? Blood pressure, you need to sit down on a seat, something like that. So they remove all the other parameters, only remain is stiffness and mass, acceleration, and then after that we solve this problem called eigenvalue problem or free vibration problem. Those of you who are taking dynamics course, they already know this. And we find from here two very important things: natural frequencies and mode shapes. So solution of this equation or this eigenvalue problem gives you two interesting things: frequencies and mode shapes, right? And this contains the heartbeat and the information that we are looking for. So if you are able to understand the meaning of the frequencies and meaning of the mode shapes, you will understand the dynamics of the structure, you will understand the health of the structure, you will understand how it will perform in earthquake, you will understand how it will perform in wind, you will understand how it will perform in moving load, whether it will vibrate. If I'm walking here, will it vibrate or not? If three people are walking here, will the floor vibrate or not? So everything about the structure's response can be predicted if we know these frequencies and mode shape information. That is a starting point for the dynamic response. If we understand this, we are a good doctor who just listen to the heartbeat and know something is wrong. You know, old days in village, people, when they don't have stethoscope, what the doctor will do, or the old, they'll just put their fingers here, listen to your heartbeat for a few minutes, and you say, this is what is wrong with you. The really good doctors could do that because they understood the beat and everything so well that they can predict your health from only that information. Now, of course, we have so many tests, so many things, but before that, doctors only had one tool, heartbeat, and they could detect everything from there. Same thing we know. If we know how to read heartbeat, a good engineer can tell almost everything about the structure that is there, that is to know, right? So that's why the most important analysis we will learn to do is the free vibration or the modal analysis. So the modal dynamic response. The modal analysis determines the inherent natural frequencies of vibration. This is the property of a structure. Does not depend on load. Just like moment curvature, just like capacity that we determined last time, they are properties of the cross section, do not depend on the load. Same is the case. Natural frequencies generally do not depend on the load. They depend on the stress state, they depend on the stiffness at any given time and the mass. That's it. Nothing else. Each natural frequency is related to a time period and a mode shape. The time period is the time it takes to complete one cycle of vibration. We will talk about that. The mode shape is a normalized deformation pattern and so on. So this is the basic definition. Let's look at this. And this is very important. Point number one. Modal analysis should be run before applying any loads or any other analysis to check the model and to understand the response of the structure. Do not forget this. When you do any analysis, even for dead load, you must run modal analysis first, because it can tell you whether your model is correct or not. It can tell you whether your density is correct or not. I have so many stories. One of the stories is that one of our engineers, very famous engineer in Philippines, he bought, many years ago, he bought ETABS from us. And then he designed a building. And then after a few months, he called me, he said, the foundation cost is too high. ETABS is giving me very big foundation. Something must be wrong in the program. I said, really? He said, yeah, the contractor is complaining, the client is complaining, why the foundation is so big? I said, can you send the model to me? Let me take a look. When we got the model, I suspected, and when I opened the program, at that time, ETABS used to use the steel as a default material. So steel density was the default, which he also applied to concrete columns and beams. So everything in his model became made from steel. So the weight on the foundation was as if it's a steel building, all solid slab with steel, column with steel. So the mass became about 7-8 times more than the real mass, and obviously the foundation became very big. Just one mistake. But had he run the modal analysis, he would have known that there is a mistake in the density, because natural period would have been wrong. And if he knew how to read natural periods, he would have immediately known something is wrong. But he didn't. And it led to foundation design and everything being so heavy, because it's making from steel everything, not concrete. Right? So that kind of big errors can be same problem on units of the modulus of plasticity. Many people make a 10 times error in the units of the E, whether it is 10 raised to power 7 or 8, depending upon centimeter or millimeter what they are using. So they sometimes do make that mistake and enter 1 0 more or less. That can easily be detected if you run modal analysis, because stiffness will be wrong by 10 times. So you will know something went wrong. So running a modal analysis is most important, and you should know how to read the modal analysis and make a decision whether the structure is okay or not. We will talk more about this when we talk about tall buildings and bridge. So modal analysis is precursor. Everything needs modal analysis. It should be run even if you don't want to do dynamics. You must run it. And then modal analysis is easy to run and it is fun to watch. That is a tall building with the modal response, right? So we will talk about it later, what this response means, right? So it's fun, but it's more than fun. You need to understand what is going on and what is right, and what is wrong, which is the first mode, what's happening now. So once you finish this course, you should be able to know what's going on in the building. It's like dancing towers. You should, if you people are going for a party, you can learn from the structure how to dance, right? See? Interesting, right? We should have a music with that actually. So each pattern is telling us many things. And if you know what to understand, you will know a lot from these videos, what's going on, right? Buildings actually do that for your information, right? So it's not artificial. So you can see it's fun, but more than fun, it has information that you cannot get any other way. Okay? That video that I showed you has so much information that if you know how to read, you can immediately see what's going on, right? We will talk about that when we go to buildings and bridges. Application of model analysis. The time period mode shapes together with animation immediately exhibit the strength and weakness of the structure. So by looking at that, you can see where the structure is strong, where it is weak, what is the weakness, what is the strength, right? It's a matter of understanding. Model analysis can be used to check the accuracy of the model. So if the natural periods are within a range, that means your building and model are okay. For example, for tall buildings, the natural period, the first natural period is related to height and number of stories. Very roughly, it should be equal to divided by 10, right? So you know that. So if the building is 20 story, the natural period should be 2 seconds. If you do the modeling and the analysis and you find that the natural period is not 2 seconds but 20 seconds, what happened? What could be wrong? Or mass? You don't know. Either the mass is too much, like the steel density, or the stiffness is too less, right? Any one of those two could be there. So then you have to check, you know that something is wrong. But if both of them are right, then what's the problem? If your model is correct, then, and you still get very high natural period, then means the building is wrong. Building is not going to survive. This building must be changed. The columns are too small, or the structure is too weak. That means you can detect the model being correct or not, and structure being correct or not, both from the model information. So when people come to us for review, the first thing we check is model response, and we can find tons of things from there. We can also check disconnected members, local modes, symmetry of the structure, doubly symmetrical, unsymmetrical, all of those, resonance. So these are the three key things. Resonance means that if the model, did you know that when the army is crossing a bridge, anybody from the army or has been to the army? I have been to. When we cross the bridge, we are told that all of you cannot walk together like this, because you walk like that. So I don't want to do that again. So when you walk, you are stepping very hard. So if 50 soldiers are walking, their rhythm of the footstep, if it matches with the natural frequency of the bridge beam, it can actually break them, because resonance will occur. And resonance can change, will increase the force by 10 times. So their weight, whatever their weight is, will become 10 times more than their actual weight because of the resonance. So they are advised to break the step so everybody does not step the same way. So resonance, dancing, floors, and some stuff like that, you have problem there. And so many things can be checked from the model analysis. Please read this carefully. We will go again into this one. As I said, this is the heartbeat of the structure. So now we know what's the heartbeat. You can also measure there's a lot of instruments now available which can measure the natural frequencies of structures. So many sensors are available now. Even cell phone can be used. They have sensors now, acceleration sensors, right? So that data can be used to determine the natural frequencies. For example, if I put the cell phone here and I do it two, three times, then if the sensor is on, it can show you, and then from there you can find what is the natural frequency of this tabletop, right? So you can actually measure the natural frequencies by using the cell phone also now. Indicate the stiffness and mass relationship. So it can tell you whether the mass is too much, stiffness is too high. So which is both very important. Basis for damping, resonance, and amplification effects. So based on this, we can then design resonance and damping and amplification can be determined from there for wind, for moving loads, for vibrating machinery. You know, when you have these generators on the foundations, it's very important that the generators, the foundation doesn't start to walk. It's called walking. Sometimes if the foundation is not designed properly, when the generator rotates, it can make the foundations walking. So the foundation can move over a period of time because the movement is such resonance that it can displace the foundation. So the design of the foundation, many things depend on this one. Mode shapes. So mode shape is a set of relative, not absolute modal displacement. So what you saw just now are the mode shapes. How the building would deform naturally. If left to deform, everybody takes the easy way out. So the building deformation or mode shape shows the most weak direction of the building deformation because it will like to deform in the most easy way. So that means if you see the first mode, it is telling you that the building will deform in this way if a load is applied in that direction. So we know the weak directions. And then if you stop the building from deforming this way, it will deform this way. If you stop that, then it will deform third mode. So if you block each mode, it will go to the next mode. For example, do we have a long ruler? Long, yes, thank you. This one. I'm sure Dr. Penning is showing you those, his table, he likes to show those. Yeah. So anyway, so this is the first mode, right, of this one. So it's the weakest direction. But if I say I won't let you move here, then in that case it will start to move like that, second mode. And then if I prevent here, it will become third mode. So depending upon how you prevent each mode, it will go to next mode. And the total response of the building is sum of all the modes, right? So we need to do that. We will talk about that when we go to seismic. There are as many modes as degree of freedom in the system. Wow, that's a lot. If a structure has 1 million degrees of freedom, there will be million modes. And normally structures have millions of degrees of freedom. So actually there are millions of mode shapes, corresponding frequencies. But we are not interested in all of them. We are interested in a certain range. One range is called global range and one range is called local range. So if I'm designing the building or you're designing the building for earthquake, we are interested in global range. But if we are designing these floor for walking, we are interested in local range. So we should be able to extract the right modes from the millions of modes. And that is a good trick. I mean, it requires some understanding. What modes are we looking for and how to extract them from the model, the relevant modes. Because in SAP, any tabs, when you're looking at the model analysis, you can specify frequency range that you're looking for. So you can be looking at the global range or local range or particular range. So you can find those frequencies or mode shapes. Not all of the modes are significant, so we should know which modes to look for. Sometimes called modal separation, sometimes called modal search, sometimes called modal identification. So this is very important. Local modes may disrupt the model mass participation. Sometimes local modes may affect what you're looking for, so you should isolate them, you should prevent them. So modal analysis is not as easy as it seems. If you really want to use this information, you need to understand how the modes work, you need to understand what range you are looking for, you need to understand what is the range which you are not looking for, and it should not come back and spoil your results, right? So there are many details about the modal analysis itself. I mentioned earlier, mode, this is the eccentric. So if the building is like that, building deformation can tell you whether the building is eccentric or not eccentric. So unsymmetry, eccentricity, discontinuity, all of the bad properties of the structure can be determined through mode shapes. Generally, this is how we look at the modes. And when you do the project, I'm going to ask you to plot your modes in the same way, same table. We'll give you a sample, we'll show you how to do that, but ultimately modes should be plotted in, for tall buildings, in this matrix, like this. So translation modes in one direction, translation modes in another direction, and torsional modes. So first, second, third, translate, weak mode, second, third, first, second, third, strong mode, first, second, third, torsional mode. So it's not just mode number 1, 2, 3, 4, 20. You need to see what is the nature of the mode, which direction it is. So you can see from here very clearly, this is the animation that I showed you. First mode, second mode, third mode. Similarly, first mode, second mode, third mode. So the animation that I showed you was actually doing that. It was showing you the first 3 modes in each direction. So that's how the nice dancing came about. So if we know what we are looking for, normally we are looking for the first 9 modes in a building. Could be more, but typically first 9 modes or first 12 modes are important for a tall building. Modal response of a structure is influenced by many things. Basically 2, mass and stiffness. Mass is influenced by structure, attachment, and occupants. So if the structure is empty, mass will be different. If it is full of people, like today, mass will be different. When it is full of water, mass will be different. If it is something stored here, mass will be different. So it's not only the mass of the structure, but also the things carried by the structure contribute to the mass, which means the natural period is dependent on the structure, whether it is full or empty, occupied or not occupied. That makes things a little bit complicated, because which means that the natural period is not a single number. It depends on when we are measuring it. Second is attachments, equipment, machinery, all those things. Stiffness. For a tall building, stiffness of the tower, stiffness of the podium, basement, foundation, and soil. All of that will change the mode shapes, model properties. So if you model the foundation as a fixed base, you will get different results. If you model the foundation with basement, different results. If you model the soil also around that, different results. So those results will be quite different. And then if somebody doesn't know this, they will think that I model the building and fix all the foundation at the column base, I'm getting a good model properties. No. Because the real building will be much different from that. And what is the effect of that? Because a lot of forces, displacements and everything will be changed because of the change in the model properties. So you are actually working with the wrong numbers. So complete model requires everything. So now another problem is that the second property is stiffness. How to estimate stiffness properly, and this is a real problem, because stiffness of reinforced concrete is also not known. We have talked about many times, whether it is cracked section, whether it is uncracked section, it is unreinforced section. What is the real stiffness? We don't know. And it keeps changing over time. As the structure becomes older, stiffness becomes? Yes. In many ways, if it is damaged, stiffness will become smaller. But at the same time, concrete strength is gained. So there is a mixed thing. So stiffness is at any given time is also not well known, and it depends how you model things and how you calculate stiffness, how much reinforcement is there. So stiffness estimation is very important, because if you estimate the stiffness incorrectly, natural period will be wrong again. And for a typical tall building, the difference between, let's say 40-story building, the difference between a gross cross-section stiffness and a cracked cross-section stiffness is about 1 second. That's a lot. 15-20% difference in this natural period can come from the cracked or uncracked section, and we do not know the real situation. That's why many people try to run model analysis for different values of stiffness. So we have one stiffness gross, we run one model. We have cracked stiffness, we run another model. Then somewhere we know this is the range. So we don't believe each number exactly, because this is not known. So we run the structure empty, we run the structure with 25% live load present, and then we look at the effect. So in a real structure, we try to study these things and then make up some judgment on what is the reliable model properties. So actual stiffness estimation is influenced by damage, deformation, cracking, creep, shrinkage, taste of stress. Many things affect the stiffness, as you know. Stress strain curve is not straight. So depending upon where we are, and also the stiffness keeps, during an earthquake, stiffness changes rapidly, very rapidly. If it's a strong earthquake, you start with an uncracked section, go to damage, many damage will occur, stiffness will change, the partition walls will break up, something non-structural component will break up, stiffness will change drastically during an earthquake, which means your response is constantly being changed. And all the analysis that you did for a particular stress state is actually not valid anymore. The earthquake force is not valid, everything is not valid, because stiffness is not, and it can be, as much as 50 to 70% changes in stiffness can happen. So that can completely change the natural period of the buildings. Make it very long, right? Or very soft. So all of those things need to be considered somehow in the analysis. So estimating natural period at various states is important. Normally, the real good way is use nonlinear models and determine the stiffness at various stages of the nonlinearity and calculate the natural period at that stage. It's a complicated process. Not many engineers know how to do it or to do it. Because you then do a nonlinear analysis, and at each nonlinear you stop the analysis here, determine the next natural properties here, then continue. So it's very complicated, but sometimes we have to do it. Apply gravity loads incrementally as nonlinear case. So this is the procedure. I can assure you, hardly anybody does that, unless it is an advanced project. It's a really important project, and it's really critical. People do not have the time to do all of that. But that is the right way to go. We can also determine from the same equation, coming back to the equation, if you want to do the earthquake analysis, you can use that equation for all types of earthquake analysis. There are 4 types of earthquake analysis that you can do normally. A static force analysis, equivalent static analysis. You can do the response spectrum analysis. You can do a pushover analysis. You can do a nonlinear dynamic analysis. You can also do a linear dynamic analysis. So 5 types of analysis you can do for earthquake, each giving you completely different results. Which one is right then? Time history, nonlinear dynamic analysis, right? That is supposed to be theoretically most accurate that we can do at this stage. So if you can do that, then you are really going as close as possible to the structure. The problem is modeling nonlinearity is not easy. It takes a lot of time, a lot of knowledge is needed. Getting the time history is not easy. So there's a lot of work to be done. It's about 10 times more work than using a linear static analysis. At least 10 times more work in terms of the effort. But you can do, normally in a design office like ours, we do most of them, not only one. We use all of them for different purposes. We always do a static equivalent also. We always do response spectrum also. We also do linear dynamic analysis. And we also do a nonlinear. Sometimes we also do pushover. Because one analysis is not enough. It doesn't tell you everything about the structure. You need to do many things to understand different things, make some decisions. So it's really, if you really want to do a detailed design, there's a lot you can do. Again, coming back, tools are there. And people who know how to do all of that can do complex, big projects. People who do not know how to do all of that, they can do two-story buildings, which is fine too, right? So it all depends on how much this equation you can apply. But the equation is the same. How many components you can handle, how to model damping, mass, stiffness, nonlinearity, and moving forces. Right? So this is all how you provide the data for each part, and after that your results analysis become more reliable. So seismic response, we will talk more about this when we go to tall building. There are also other analysis that you can do. You can do a P-delta analysis, you can do a buckling analysis, static pushover, fast nonlinear, large displacement, free vibration, response spectrum, steady state. There are many more that also come from the same equation. So if you look at SAP, for example, now SAP 2000, there are about maybe 22, 23 different types of analysis that you can run on a structure for determining various response, all based on the same basic equation, but considering different factors. For example, buckling is the same as modal analysis, but uses a different way to solve this thing. It does not use the mass, it just uses the stiffness of the structure with no load. Determine buckling. Similarly, large displacement. That means it not only modifies the stiffness of the structure from the previous load, but also the geometry. So if you want to model a falling body or a falling structure completely, then you need to do a large displacement analysis, which is a special kind of nonlinear analysis. Right? Similarly, many types of analysis can be done. So the trick is to learn these analysis options and see what data is needed, how to carry out, how to interpret the results, and how to use it in real situation. So for the same model, more or less, you can run many types of analysis. Seismic analysis procedures, there are four main categories: linear static procedures, nonlinear static procedures, linear dynamic procedures, and nonlinear dynamic procedures. So you can do 4 levels of seismic analysis, earthquake analysis, and we will talk a little bit more about that. Not all of them we can do in this class, impossible, but at least we will introduce a little bit. Mostly you will be doing linear static analysis and response spectrum analysis, linear dynamic analysis. So you will be doing this one for your project, and you will be doing this one for your project. You can also do this one if you are a little bit more adventurous. You can also do, it's easy. This one and this one is, both of them are not much different. So if you like, you can also run this one. But you cannot do this one. This is too complicated. You can do it in a thesis. So most of the students who are interested in this procedure, they do a thesis on this subject. And in the class, we will do this one, and we will do these two you can do. And this, you can take a thesis if you are interested. So nonlinear time history is advantage is that it applies to all types of structures. It accounts for everything. Nonlinear dynamic time history is the best one that you can do. So if you learn how to do nonlinear dynamic time history analysis, that means you are at the forefront of structural engineering. And not many people are capable of doing that or are doing that regularly, let's say. So estimating, understanding, and including dynamic response in the design is the key for high and reliable performance of structures for wind and earthquake. It all starts with model analysis. So remember this statement. So if you want to do a really good analysis and design of buildings or bridges, you need to learn dynamics, you need to learn nonlinearity, and you need to start with model analysis. Right? Any questions?